So the first speaker of today talk is Bhavanesh BS. He is an MSc student from IIT Kanpur. It seems he attended level 1 in the last summer camp. His topic of presentation is commutator subgroup of a group. So now I request Bhavanesh to present his talk. Over to Bhavanesh.
Thank you, Professor. Glad to be here. This talk is about commutator subgroup. The goal of this talk is to find for any given group G, find a subgroup G dash such that G mod G dash is abelian. Like we are doing this because abelianness is so simple and unique. Like as Janvi just said that if abelian we have a complete classification of everything, its structure. But since there are a lot of different and lot of diverse varieties of non-abelian groups, we would like to create a measure for something, measure for a group, how far it is from being abelian. So let's first just ponder upon the question: is this even possible? Yes, at the very least, if no subgroup works, the whole group itself will give the identity which is abelian. That is a trivial group which is abelian. So this question is well defined. That is, we are completely good to go. So we will build the group by first finding a few properties of the group. So maybe to get us few hints. So recall that this notation G mod G dash, the quotient group, means the set of all left quotients of G. So if this is abelian, then for all x and y in G, we must have this. For all x and y in G, we must have this xg dash into yg dash must be equal to the yg dash into xg dash. But since for this to even make sense, g dash must be normal. So we write xyg dash equal to yxg dash. But also we know that if two cosets are equal, if ah equal to bh, then a inverse b must belong to h. By that fact, yx inverse times xy inverse will belong to g dash. Using this, if we expand this, we get that for all x and y in G dash, we must have this. So what have we started? We assume that G dash must be such that G mod G dash is abelian, and we have a condition that this must always hold true. Let's first name this guy something because this is what we'll be working with. So I will call this type of element a commutator. A commutator is any element of the form x inverse y inverse xy for some xy in a group. Why is it called commutator? Because if the group is abelian, then what will this be? X inverse y inverse xy will always be trivial. That is identity, right? So the group commutes, then it is identity. So if it not commutes, then it has some other value. That is the motivation for naming it as a commutator. So now, if we collect all the commutators, will it be a required group? Let's check. Like, will first for a subgroup, what all the conditions must we have? Like, what are the things we need to check if G dash is a subgroup? First, we need to have an identity. Is there an identity here? Audience can will identity always belong to G dash as I defined it here? The set of all x inverse y inverse xy. Will identity belong to the set? Anyone? Okay, yes. So I will say yes, identity always belongs to a set because if we let y to be just the identity and x to be any element, it will always be identity. So identity always belongs to, I will write this. Identity always belongs to G dash. So this is fine. But what about closure? So a group must be like with identity and it must be closed. But unfortunately, as it turns out, sadly, the product of two commutators need not be a commutator. That is, this set we defined is not a group. It is not even closed under the operation. And also the first I mean by listing the orders, the first group in which this happens is of order 96, which is sad. So this just reasserts the fact how important proofs are. Just because we work it out for some first 20 or 30 groups and the groups get more complicated, we cannot just say that it must be closed. Count this notion of smallness and largeness of numbers is just a human measure. So we need to be absolutely sure. That's why we use mathematical rigor. More on this later, but sadly this is a very slightly involved example, so I will not prove this here, but I will talk about this later. So if this is not closed, then what can we do? So then G dash must be the all the group generated by all commutators. What do I mean by that? By that I mean the smallest subgroup of G containing all commutators. Like whatever it is, it must contain all commutators. Only then will the condition we found above will work. All we said that all commutators must belong to G dash, right? That is one thing. So G dash in addition can have extra element. By extra I mean that whatever elements that are required to make it a group. This notation is called the element generated by commutators. Okay. So just to be sure, we will double check if this is normal as required because we have just found the definition just to be sure. So it is what is the required criteria for normality? Subgroup is said to be normal for all G in G and H in G dash. We must have G H J inverse belongs to G dash, right? Note that if we show the following thing, G H J inverse H inverse into H belongs to G dash, then that will imply our original claim because we've just introduced H inverse for our convenience. Why am I introducing this H? Because I see that this is somewhat close to the general form of a commutator we have defined. See, it is just the inverse of a commutator. But since we have said that G dash is a group, it is closed. So every commutator will have an inverse. So this inverse also exists in G dash. So this belongs to G dash. Oh, sorry, this means that this belongs to G dash, and also H belongs to G dash by assumption. So then we have G dash is normal. So there's nothing wrong. So what we have found is indeed the commutator subgroup such that G mod G dash is abelian. That's a nice thing. Like if okay, a question for the audience. If the group G is abelian, what will G dash be? Can anyone answer? We are going to go into examples. Before that, I want the audience to answer a simple question. Like, if G is abelian, what will its commutator subgroup be? Any abelian group.
It will turn out to be identity.
It will be?
It will turn out to be identity because it will commute and X inverse X will identity, Y inverse Y is identity.
Exactly, Priyanshi, well done. You're right. It will be just be the identity. So for abelian groups, we are all clear. It will just be the identity. So we'll go on to some other more examples. I have taken a few natural and simple examples. First example being the S3, the symmetric group of 3 elements. Why is this natural? If you think about it, I want to go into much detail, but the thing is that S3 can be thought of as all the possible shuffles of a card, like all the possible way to shuffle 3 cards. So when we talk about the notion of symmetry, this is the one that turns out to be a lot prevalent and all encompassing, if you will. So I took a G dash I taken this G dash. Like I'm not okay. I am taking this subgroup 1, 1, 2, 3, and 1, 3, 2. This is normal in S3. Can anyone say is there a normal subgroup of S3 with order 2? If you guess, we can, like okay, like we can just give. Suppose if you take 1 and we'll take this subgroup of order 2. We'll take 1 and 1, 2. This is a subgroup of order 2. Everyone agreed. So, but this is not normal. So, if we take G, this element 1, 3 inverse will turn out to be 2, 3. It won't belong here. So, we can find out that any subgroup of order 2 cannot be normal. So, it must be of order 3. And there is only one subgroup of order 3 in S3. That is this. This is normal too. So, the quotient makes sense. So, automatically we will have that this is isomorphic to Z2. Why am I saying this automatically? Because S3 has order 6, right? The number of ways to permute 3 elements is 3 factorial 6. So S3 has order 6 and G is a normal subgroup which it has order 3. So this quotient will have order 2. It will always be a group because the quotient is well defined. So and also there is only one subgroup, one group of order 2. It is Z2. So this G dash guy is the commutator subgroup of S3. My next example will be D8, the set of all symmetries of a square. So again, I have taken the example directly, but let's ponder like why I took this example. First of all, if I can find a subgroup, normal subgroup order 2, I will be done. Why? Because If I find a normal subgroup, the quotient will make sense, and the order something. And the order of this quotient will be just 8 by 2 or 4. And we know that every subgroup of order 4 is abelian, so it will be done. We just need to pick the right subgroup. This is one subgroup order 2. Let me just clarify the notation. Here R means a reflection of 90 degrees, and S means, sorry, I'm so sorry, I mixed terms. R means a rotation of 90 degrees clockwise. 90 degree clockwise, and S is a reflection. Okay. A reflection about let's say XY axis. So that is, if you consider square to be on this hill, I'm considering the reflection to be, oh, I did not mean XY axis, I meant X axis. X axis. So the element what it does is that it reflects the square, the symmetry reflects it this way, and R is a rotation, 90 degree rotation this way. Okay, so that is the notation. So can anyone give me another subgroup of order 2 of D8? This is one subgroup, because R square whole again it will be squared, it will be just identity. So this is a subgroup. So can anyone give me another subgroup of order 2 of D8? Okay, the another subgroup is 1, S. S being the reflection as mentioned. Since S is just a reflection, if you do the same reflection twice, we will be back to the original space now. So this S has order 2, so therefore this is an element of order 2, but group of order 2. But unfortunately, this is not normal. Why is this not normal? You can find a counter example. One counter example is that you take SR, you take G equal to SR and do this SR inverse. Let's do this. I'm not sure if you are comfortable with the notation, maybe use a different notation, but with this we'll go on. So this will become, first let me evaluate this. The inverse of SR is just SR is a reflection, so it will be itself. So this will be SR into R, because S square is just identity. So this is SR square, which is not in the group. So this group of order 2 is not normal. So only this group of order 2 is normal. So this is normal to D8. So if we take the quotient, then we will get this group. Why do we get this group? Because like in this quotient, for this I need to list out the elements. I will list out the elements. Give me a second. D8 has 1 R square, R cube, S, SR square, and SR cube. These are the elements of D8. So in this R square and SR square, if I match, this will be identity and these all will be identity. So the remaining elements will only be G dash, R G dash, S G dash, and R cube will just be R. So then SR G dash. So if you do the quotient, you will get this is thing. Why am I doing this? I'm doing this to find out which group of order 4 this is. So initially I said that if we find a normal subgroup of order 2, we will be done, because every group of order 4 is abelian. So I'm trying to find out which abelian group it is. There are 2 abelian groups, like Z4 and Z2 cross Z2. So it turns out, doing this computation, we find out that every element is of order 2. So if you perform the same thing twice, we will have R square G dash, but R square already belongs to D dash independent, so it is an identity. Similarly, every element will have order 2. So this group is of Z2 cross Z2. So also working with commutator subgroups is a good exercise to build up your algebra. See, we define the commutator subgroup as the group generated by all commutators. If you try to substitute each x and y and find each commutator and find the group, it will be very cumbersome. So I have to do what, like if D8 has 8 elements, then I have to do 64 combinations. And 64 combinations, I have to find out if it's a group. So using such extra group theoretic concepts, we can be more efficient. So that concludes the example part. Now to the main part. So commutator subgroup is like the one strict PT teacher we all had at school. So if that PT teacher is in the class or anywhere among group students, those students will be the most quiet in the whole campus. So this G dash is that PT sir. Why am I saying this? I'm saying this because if we take abelian to be the quietness, then if G mod, this is a theorem, I will prove it. If G mod H is abelian, then that PT sir, G dash must be a subgroup, must be amongst H. So in this way, G dash is the smallest subgroup that makes G abelian. We will prove this claim. So we will first go to this direction. We will first go to this direction. So since it is given that G mod H is abelian, for all x and y in G, we must have this. Again, we did this already, but the only thing is that this does not conclude the proof. Showing that every commutator belongs to it does not conclude the proof, because G dash is not just the commutators, it is a group generated by commutators. But that is not a big problem, because each commutators belong to the subgroup implies that the G dash, it's all its generators belongs to H2. Why? Because it follows from closure property. So G dash must be a subgroup of H. So one direction is complete. Now the other direction. I'm saying that if the PT sir is amongst the group, then the group must be silent. So for all x, y, and G dash, we have this. We're just trying to find out what happens to G mod G dash. So I'm taking an element for any for arbitrary x and y. I'm taking x G dash times y G dash. This will turn out to be this because G dash is normal. And then I can rewrite this guy xy as yx times x inverse y inverse xy, because these guys just cancel out. But this we already know belongs to G dash as it's a commutator. So we'll have yx G dash. And since G dash is normal, again we can split this. But wait, our x and y was arbitrary. So this holds true for any x and y in G. So G mod H is abelian. So we concluded that we concluded both parts, if and only if. So if G mod H is abelian, then if and only if G dash, the commutator subgroup, is contained in H. This is what commutators, this notion of uniformity and relative behaviorness is what makes commutator subgroup a nice concept. So with that, I have a small question to do for the reader, and I will conclude. We will not do this now because it will take a little more time. But the audience can take this question up if they are interested. So if for any group G, if G power this notation 2 is defined as the group generated by all square elements, like generated by x squared such that x belongs to G, then is the commutator subgroup contained in this? That will be a question for the reader. So also the purpose of this talk was to introduce the notion of commutator subgroup to the audience, and if the audience is interested, they can look up a little more on, they can develop their algebra to this. So through this, so if they want, they can read about semi-direct products and can actually construct this group of order 96 themselves. So with that, I will conclude my talk. Thank you all.
Yeah, thank you, Bavanesh. Do you have any questions? Okay, if there are no questions,
so one thing.
Yeah.
So say some. So anything like say you have a group and you cannot use commutator subgroup. Okay, how can you give some ways to find out some possible subgroups with which we present and get abelian groups? So my question is, say someone don't know how to handle commutator subgroup. Okay. Am I audible? Bavanesh?
Yes, you are sorry.
Yeah. So the question is, without using commutator subgroup, can you produce some G dashed so that G quotient G dashed is abelian by looking at the order of G? I mean,
Without commutator subgroup, the whole group will always be the whole group will always give a trivial quotient group, but the commutator subgroup is just the smallest subgroup that does this. So also one more possible way to do that is that if if the order of G is even, then if we find a subgroup of order index half, that is, I write this down 1 second, give me a second. So we can do this in this case. So suppose the order of G is even, then if we find a subgroup such that this is exactly 2, then automatically H will be a normal subgroup. And further, since this is 2, this will the quotient group will be isomorphic to Z2. So in this way, we can find such a group. This will satisfy the G mod G dash is abelian, but it is not necessarily the smallest subgroup that it happens.
Yeah, correct. So one thing is this. So actually, it could be generalized, na? That index is a prime and P is the smallest prime dividing.
Yes. If G, the group is the order of a group is G dash, and if there is a subgroup it's such that G order of G divided by order of H is P, where P is the smallest prime dividing G order of G, then this H is normal. In fact, that is what I used to guess my first example. In the example, I took S3, right? So a symmetric group. A symmetric group is of order 6. So what is the smallest prime dividing 6? The smallest prime dividing 6 is 2, right? So 2. So if I can find a subgroup H such that order of G divided by order of H, the smallest prime is 2, right? So H must be 3. So if I can find H of order 3, then it will automatically be normal. That is the motivation to directly jump into groups of order 3.
Yeah. So actually, why I asked this question is, like, this is not the case that we don't have tools in our hand. We already have some tools, but these tools are not giving me the smallest subgroup always.
Yes.
But your commutator subgroup, this is that more concrete tool, right? Yeah. That's where importance of this commutative subgroup comes. Yeah, that's it. Thank you.